Okay, so when you look at Saturn, for instance, and the famous rings, what you see is planets, planet Saturn, some moons very far, no moons very close. And what do you see very close? Rocks. These are destroyed moons. These are moons that couldn't handle the tidal force, and they broke apart.
Okay? I never knew that.
Okay, so this is, you can do a simple model. Imagine you have a moon made up of two spheres connected by something, by a rod, and try to calculate what is the force that tries to separate the two spheres, compared with the force of gravitation between the spheres to keep it together. And you can show that the particular distance, one dominates for the other. And everything that is inside that radius is a famous radius, has a name and all that, will break apart. Everything that is outside has a chance to stay together. Okay, so when you look at and this happens particularly for very massive planets. That's why you don't see it in the Earth, because the Earth is not very massive. Okay, so the
Saturn, like way bigger.
Saturn, Jupiter, they have multiple moons, and the moons that are surviving are the ones that are far enough that the tidal force doesn't have enough strength to break it. Okay, and that's the reason why the moon, our moon, is stable. Is because we are about 60 radius. The moon is about 60 Earth radius from the Earth. Okay, and the front side and the back side of the attraction is very close. They are not very different. Okay, so the effect is on the moon is a very small stress. There is a tidal force on the moon due to the interaction with the planet Earth, like Jupiter with the moons. But because of the distance, the moon is in the far side of that limit, it doesn't break apart, which is nice, because if we didn't have a moon, besides all the nice thing that happened with the sky at night, the moon has a stabilizing effect on the orbit of the Earth. So if we don't have moons, it's more likely that the orbit will be unstable. And there are all kinds of studies made about the more moons you have, the more stable is your orbit as a planet. Okay.
So should we make another moon for ourselves?
See, you should make it. And we actually believe that our moon came from the Earth. Was basically a collision with a giant, asteroid or something that broke apart a piece of the moon, a piece of the Earth, and ended up in orbit around the Earth. Okay.
Why is it so circular then?
It wasn't.
How did it get circular then?
Yeah.
Well, I mean, basically, circular happens because there is a tendency for the object to find. Basically, the idea is this: if you have many rocks, okay, that need to coalesce to make a moon, you don't have a moon when you start with. You have a bunch of little rocks, and what happens is they are orbiting. It's like you have orbiting, but because they happens very far from the Earth, the gravitational attraction starts basically putting together the rocks into a sphere, okay, in a process that takes millions of years. So the moon was formed by accretion, by basically you blow up a lot of rock, okay? You don't blow up a sphere. Yeah? When you get this is like putting a bomb, okay? You get all these fragments flying around. At some distance from the Earth, the orbit is pretty stable because the tidal forces are small. And then the gravitational attraction of the different pieces of rocks starts putting them together. So they start coalescing, okay? Eventually, the bigger the rock is, the more it coalesces the other rocks that are in the same orbit that are not part of it. And eventually becomes, Now, why spherical? It has to do with stability, okay? Most astronomical objects that are stable are spherical, okay? It's simple because if you have a piece of the object that sticks out, it's going to be attracted more than the rest. So eventually will be kind of flattened, basically. That's it. That's why you don't have very tall mountains, because they are unstable, basically. If you have a mountain that sticks out a lot, then the attraction of the rest of the planet on the orbit tends to flatten. Okay? So the spherical form is basically the final result of all these geological processes because of the.
Is Mount Everest not considered to stick out a lot?
No, compared with the radius of the Earth, is like a little bump. I mean, you have 6,300 kilometers is the radius of the Earth, 6,370 kilometers radius of the Earth. How tall is the Everest?
Like 6,000 meters.
Yeah, so let's say 10 kilometers. So we're talking 10 kilometers in 6,307. Okay, so 1 in 600, 1 in 700. So that's a bump. That's a bump. That's not very meaningful. And eventually, those rocks will tend to flatten. I mean, the Everest is not going to stay like that forever. The general point is that these things tend to erode and tend to be flattened by the attraction of the rest of the planet. Okay? So you have very explosive events, magma events, things like that, that create these abnormal surfaces. But then the slow process of gravitation tends to bring it back. So that's the idea of these tidal forces. Okay, they are not only creating tides when you have water or a fluid, but if you don't have a fluid, then you have the stress on the material that breaks apart, and it's a very big part of the history of the different parts of the solar system. Is how did they end up in this condition today compared to what they have? The other thing, of course, is do you know if the solar system is stable? We think it's stable because it has been around for a while. But actually, when you look at the mechanics of the solar system, it's not stable. The fate of the solar system, regardless if the sun is there or not, much before the sun has a chance to start basically disappearing because the fusion runs out of material. That's the end of the star. When the fusion, the fusion of the star keeps it in balance from collapsing gravitation because it's a gaseous thing. So basically, if you don't have something that creates basically energy in the star, then the gravitational pull will end up making it smaller and smaller until they become, basically sort of a black hole. So the idea is that that basically before that happens, which is going to happen when the sun dies, it's going to take another 5 billion years or so. Before that happens, the solar system is predicted to be unstable. So basically, it's going to the orbits will start moving away from circular, and they're going to start breaking bigger elliptical, and eventually they're going to move away. We don't have to panic. I don't intend to be there in 6 billion years to witness it, but it will be something interesting to see. So that's the idea of this chapter, is calculating gravitational interaction between typical objects. And the typical object, remember, is the ring, the disk, and then the plane. Okay, those are the three main objects we would like to know. Of course, we don't have flat planets, okay? That is a plane, but it's an important special case. Why is that? Because in many situations, because the material is formed by rotation, okay? You have a large region that is comparatively thin, okay? It's a thin grid, so it looks like a disk. So in many galaxies, what you see is a disk shape. The material is not in a spherical shape, it's in a flat shape, like the solar system is. That most of the planets are in the same plane, okay? Same plane. We don't have different planes for Earth, Mercury, Venus. They are all pretty much in the same plane, okay? And that's also part of the stability, okay? The fact that if the planets will be going in all directions, then that will be terribly unstable, okay? Because when a planet comes close, it will kick you out of orbit, and then you can't get back, okay? So basically, what is durable, what is stable, is this kind of situations in which the material is in a plane, in a disk shape, not in an extended in both directions, okay? And under this condition, what you want to know is if a mass is nearby, does it get attracted or not, and how strong? Okay, because as you know, these are like big blobs that swallow material. Once you have a pretty large mass, you start growing now because that gravitational attraction pulls any other object nearby towards it. Okay, so this basically the massive gets even more massive because of that process. Okay, and this is an example to calculate. Okay, with what force is this piece of mass being attracted to this ring or now disk? Now this is a disk, uniform disk of mass m, but we calculated by calculating the attraction of a ring, okay, and then adding all the rings from 0 to big R. Okay, this is the same calculation we do in E&M when we calculate the electric field due to a disk of charge. Okay, it's the same calculation, exactly the same math. Okay, and then what we do is we extend the radius to infinity to obtain the gravitational pull of an infinite plane. Okay, do you not have any idea what is the gravitational pull of an infinite plane?
Infinite plane?
Infinite flat plane.
Infinite.
Do you have any idea? Do you have any idea what was the electrical result? If I have a very large plate of charge, what is the electric field around it or near? Imagine I have a 100-yard by 100-yard metal piece with, or not metal, but charges distributed uniformly, and I'm, 1 yard away. What is the field I feel?
0.
Do you know? No, it's not 0.
Sorry, would you repeat that again? The question.
What is the electrical attraction between a positively charged large plane and a negative charge plane?
Oh, the positive and negative?
Q.
Well, we want attraction because gravitation is attractive. We want to look at an electrical case that is similar. So, for instance, the plane is positive and the mass is attracted to it. Well, the plane is positive charge and we have a negative charge that is being attracted. How big is the force?
Wouldn't it be Q over R?
Nope.
For infinity?
For infinity, the first thing is, does it depend on the distance?
No.
If it's an infinite plane, no.
Infinite plane, the force does not depend on the distance in the electrical case. Do you remember how it depends? On what does it depend?
It depends on like the magnetic
orientation, right?
No. I have a flat, very large plane, and I'm looking at a point nearby, a few meters away, for instance. What is the amount of force that is going to attract the negative charge to a positively charged plane? What is the calculation?
I don't know. Minji took E&M.
Oh my God, Minji, they're sending you to the front.
Well, we all took modern.
Now, I'm sorry to say, but this is 104 material.
Oh, isn't it something times like Q times Q over
remember, this is an infinitely large plane. What is the main property regarding the charge? The charge is infinite. The area is infinite. What is the property that makes sense?
It's evenly distributed over all the charge.
Yeah, so it's the charge divided by the area. It's the thing that matters. Okay? So if I have an infinite amount of coulombs in an infinite amount of meter squares, what matters is the density of charge. How many coulombs in 1 meter square? Okay? This is usually called sigma, charge per unit area. Remember those days when you took 104 and then 204 and then all the others? I know you were young.
A couple millenniums ago.
You were young and impressive in those days, but impressionable. So
that was like last decade.
Yes.
It's sigma over 2 epsilon naught.
Yep, exactly. sigma over 2 epsilon naught. All right, so the idea is, how would you do that? Well, you can apply Gauss's law and use a kind of a pillbox that has one lid above the plane, one lid below the plane, and some cylindrical walls, and apply Gauss's law that the electric field flux is equal to the charge inside divided by epsilon naught. And from there, you get that the electric field is sigma over 2 epsilon naught. And it doesn't depend on the distance. Well, in the case of gravitation, it's the same thing. The gravitational G, the gravitational field, it comes from the density of mass, the mass per unit area, okay? And you have, instead of epsilon naught, what do you use? We're trying to recycle a formula. We have a formula for electricity. We want to recycle it so it will work for gravitation. So
we use G, right?
Well, for electrical, we use epsilon naught in the denominator, sigma over 2 epsilon naught. What will be the equivalent for gravitation? What is the equivalent of epsilon naught in gravitation?
It's the big G, right? Or it's like
the big G
times.
Basically, what in one formula is 1 over 4 pi epsilon naught, which is the constant in front of the q over r squared. In the other one is what? What is the expression for the gravitational force? Do we have a 4 pi somewhere?
Let's see.
What is the gravitational force? Big G?
6.67 times.
No. Yeah, well, I mean, big G, and then what? The gravitational force between two masses.
That's it, right? It's just big G, right?
Well, big G is a constant, so cannot be that.
Oh, little m, big M over R.
R squared.
That's what you meant. Oh, yeah. That's
the force between two masses is GMM over R squared. G is not 9.8, okay? G is the big G, okay, the gravitational constant. So what in one case is GMM over R squared, in the other one is 1 over 4 pi epsilon naught, QQ over R squared. So what the analysis is the same if you do the similar departure. So basically, 1 over epsilon naught, because epsilon naught is in the denominator, appears in Gauss's law, sigma over 2 epsilon naught. That means it's going to appear as a big G in the numerator, okay? Because it appears in big G in the numerator in the force equation, the similar equation. So what in one case is 1 over epsilon naught, in the other one is G in the numerator. So basically that's the difference, okay? So you can calculate basically what will be the gravitational field of a flat plane of mass by knowing what is the result for the flat plane of charge, okay? And it has to do with the density of mass per unit area, okay? And the gravitational constant. There are exercises at the end of the chapter that discuss that. So you might want to pay attention, all right? This is the main part of the chapter. Keep in mind the idea of force versus field, okay? Force, GMM over R squared, field, force divided by mass, where mass is the mass that is being acted upon. Okay? And then the potential being such that the gravitational field is minus the gradient of the potential. Okay? So, exercises you want to work on your own. I hope that you will, I don't expect you to do the math in the test of the tides, but I do expect you to be able to estimate the tides based on this GMM over R cube, okay, and so on and so forth. And this is the predicted height of the tides, about 0.5 meter. That's the average tide. Of course, the local tides can be much bigger because it depends on if it is a bay or is a enclosed area or is a exposed area. All right. So exercises, you have a ton, okay? 5.5 could be interesting to work, okay? So you have an object falling from very large distance without a resistance and calculate.
We love that.
Okay.
Collecting air resistance.
The same 5.7 gravitational potential due to a rod of mass at the distance and from the center. So basically, you have a rod and you have a point here in the midplane, okay, in the R from the center of the rod, and you can be at the distance here or in the line of the rod. Okay, you can have both cases. So how much attraction you get if you are here, and this is a rod of mass m? How much are you attracted? So you treat each piece of the rod as a point mass that attracts with the force G mm over r squared, and then you integrate all the contributions. Okay, of course, the ones that are close contribute more than the ones that are far. This is exactly the same that this will be a line of charge instead of a line of mass. The same math, because both go like 1 over r squared. Okay? So that's 5.7. The potential due to a ring, we talk about it. You might want to review the calculation. And then this is a problem that we made. I think we talk about it. Problem 15 is if you drill a hole through the earth and you drop an object, you can show that the motion will be like a spring motion. It will oscillate. Okay, so if you drill a hole through the center of the earth, imagine you could do that. Okay, and you drop a mass from the surface of the earth where the hole starts, what will happen? Well, as the object moves in, the part that is attracting the object is only the mass that is inside of the radius where it is now. Remember, if you have a shell and you are inside the shell, it doesn't attract you. If you are a shell and you are outside the shell, it attracts you with a force equal of a point mass at the center. Okay, so you have to imagine the Earth as like an onion with a lot of shells on top of each other, and as you go through the tunnel, different amount of masses are inside your ring. So you can calculate what it will be the force created on you by a mass that is uniform, which is not the Earth, but ideally is treated as assuming that the Earth is uniform. Okay, and you can show that the force is proportional to the distance to the center. Okay, when you look at it, why is that? Well, because the force of a point mass goes like 1 over r squared, but the mass that you have goes with r cubed in a sphere. So the net result is that the force goes with the distance r, which is exactly like a spring system. That the force is proportional to the distance and attractive with the negative sign. So it behaves like a harmonic oscillator. Surprisingly, a mass drop through a tunnel on the Earth will behave like a harmonic oscillator, meaning it will, if you start from rest, it will speed up as it goes through the center of the Earth. Once it passes the center of the Earth, what will it do? Slow down, because it's been attracted on the other direction, and then eventually will stop on the far side of the Earth. Okay, how long does that trip take? It says that it takes 84 minutes to do an oscillation, basically meaning coming back. That means it takes 42 minutes to go to the other side of the Earth. And this has been something that people have talked a long time, that a good way to travel, it will be, instead of flying from point A to point B, will be to have tunnels that could take you from A to B directly to the center of the Earth. You have a small problem, it would be an incredibly difficult tunnel. And second problem, you will have to go to a very hot center of the Earth that will probably give you a tasty feeling of 5,000 degrees or so. But it could be done on a place like the moon, if you had a colony in the moon, people have basically proposed, if you have a place like the moon that doesn't have a hot core, the moon is just a cold rock everywhere, okay? It doesn't have a magma, it doesn't have volcanoes, it doesn't have all of that. It's just a bunch of rocks put together. If you could drill a hole through the moon, to the center of the moon, then you could go from one side of the moon to another without, not only without flying, because you don't have an atmosphere, it's very hard to fly, but not only that, but it will be a zero cost. Okay? So this motion to go from one side to the other will be gravitation. You don't have to have any fuel to do it. Okay, so that will be a reasonable way to create a system of transportation. Drill holes on the sphere and let you travel across instead of around the ocean.
Wouldn't you get it going like incredibly fast though?
No, it's not too fast. You can do the numbers. Notice we are taking 42 minutes to go from one place to another. So this is not, of course, it's fast, but it's not something that you're going to fall apart. Okay. But it will be a very interesting trip to do. Okay. So you might want to do the calculation and show that effect. Of course, it's done in your homework in the solution, but just go through the calculation. Okay. Because you might have.
Is that important information?
Yeah. This is a problem that's also useful, is the tides taking into account. This is a detail that people that started to do the first person who tried to explain tides, who was that person?
Newton.
No, Galileo.
Galileo.
Oh, Galileo.
Galileo,
But
bro.
Newton was the first one to give a correct interpretation of why you have to.
That's what I was thinking of. That was a trick question.
Yeah, and also the fact that because the moon rotates, okay, in the same direction than the Earth rotates, then the tides don't happen every 12 hours. There is a 12 hour and 26 minutes between high tides. Okay, so if the moon wouldn't rotate, the only thing that you're dealing with is that the Earth is rotating. So half a day later, you get the same effect. And then, so every 12 hours, you get a high tide. Because the moon rotates, you get an additional 26 minutes between high tides. And that's something that it was curious that if you measure the high tides, the next high tide doesn't happen 12 hours later. It happens a little bit later. That has to do with the moon rotation. So you might want to look at the discussion and try to figure out why is that, and of course you have the solution, so you can find that out on just like that. Okay. So I want to just mention these 5 minutes, and then we call it a day. Okay. Chapter 6, 7, and 8 are basically, chapter 6 and 7 actually, are associated with the introduction to the alternative formulation of mechanics. Remember, we talked at the beginning of the semester that we have the Newtonian formulation, okay? That's all what we saw so far. And then you have this, which is the Lagrangian formulation, okay? So to get to chapter 7, which is very thick chapter, I would like to move pretty fast so we can see that. So what is the deal? Every problem we were able to do using Newtonian mechanics, it should be doable using Lagrangian mechanics. Okay? So one of the things in the final exam will be solve the problem using Newtonian mechanics and solve the problem using Lagrangian mechanics. Now, why would you want to have two methods to solve the same thing? Well, Lagrangian mechanics is particularly good the more complicated the problem is. So nobody uses Newtonian mechanics for complicated problems. Okay? So Lagrangian mechanics is the more powerful formulation. Okay? They all start from the same principle, but the methods they use are different. Okay? So we will have to review how to do the old problems using this new principle that is equivalent but is a different principle. It's called a variational principle. Okay, variational principle. So in chapter six, we look at calculus of variation. That's calculus of variation. Okay, so calculus of variations is a branch of mathematics. Okay, that tries to answer this question. Okay, if you have many ways to do something, what is the particular way that will minimize or maximize a quantity associated with this motion or this problem? You can formulate quantum mechanics that way, for example. That was Feynman's theory. It's all based in calculus of variations. Variation means if I have slightly different ways to do something, which one is the best way? Okay, which one is the best way? And the idea is the following. The initial problem that started off, it's called the Brachistochrone problem. So I'm going to just show you this. And then next class, after the test on Monday, we'll talk about the particular examples. But just to give you an idea. See if I can find the page. Okay, so this is the problem. It's called the page 212 in your book. The Brachistochrone problem. This Brachistochrone. So basically what this is, maybe I should go a little bit bigger. Not that big. Okay. So what is the Brachistochrone problem? The idea is this. This is a vertical plane. Okay? This point toward the floor. You have a starting point. Imagine this is the blackboard. Okay? You have a starting point and an ending point under gravity. Okay? Imagine that you know that they have in these waiting rooms in doctors' offices or dental offices that you have a wire that you can shape and then a ball, a little bead, can slide down there. Have you seen these toys?
Yes.
You have a thick wire that you can shape in any shape you want, and then you let a bead that has a hole to slide in. Mm-hmm. Okay, imagine that's the situation. What shape would you give to the wire so that it goes from the start to the end in the shortest time?
Just a straight line.
Straight line.
Not, I didn't say short distance. I said the shortest time. Okay, so how do I go from here to here in the least time? Not the least distance, which is a straight line. The least time.
Least time.
Least time. Which will take you less seconds from all the possible alternatives. Of course, you can shape it with this a little bit that way, with this a little bit this way, with this starting horizontal, starting vertical, starting in between. What shape do you give to this wire so that it takes the least possible time to go from here to here? Why do I say that the straight line is the shortest distance but not the shortest time? Because when you start, okay, you start from rest, okay? So it takes time to build up speed. It takes time to build up speed. So maybe what you want is something a little bit more extensive path, but that gets you gain speed faster. Okay, it's a game of speeds. So the idea is that what you want, instead of going straight to the end, you want to start going down first. Why? Because when you go down first, you gain more speed
faster.
And then you head that way. Okay? Actually, this was proposed as a contest by a guy called Bernoulli, which comes from a very large family of geniuses of math and science. And Bernoulli knew the answer. Okay, he had worked it out, so he posted this as a problem to be solved by the geniuses of the time. Okay, and the geniuses of the time of Bernoulli, one of them was, of course, Newton, that was living at that time, another one was Leibniz. Leibniz, the other creator of calculus. And they were supposed to submit answers to find out what it is. Okay. What do you think is the shape?
Doesn't it not matter?
Doesn't what?
Doesn't it just not matter
Oh yeah, it
what
matters.
shape it's in?
Oh yeah, different shape that give you different time.
Oh.
For instance, if you go horizontal and then vertical, you never make it. Because you can move, you go start horizontal. If you go vertical and then horizontal, you can make it there. But then you're doing a lot of travel compared to the hypothesis. Okay? So you can imagine that straight paths are not a good idea. Direct path looks good, but it's not. Okay? And in general, you have to find some curved path. Okay? Now, this was the problem that started the field of calculus of areas, then expanded into all kinds of areas. So what you're trying to find is not what is the least time, is what is the shape that has the least time. So what you're trying to find is the function y versus x that minimizes the time. How do you find the time? Well, the time to go from here to here, let's say, what is the time? Well, is the distance divided by the velocity. Okay? So it takes a certain amount dt to go from here to here, which is the piece of length, ds, divided by the velocity. It takes another dt to go from here to here, from here to here, from here to here. Whenever the velocity is quick, that is done in a short time. Whenever the velocity is small, that takes a long time. So you add all the times, and you get the total time. Okay? So basically, the only thing we're trying to solve is this thing. Okay? What is the total time? Is the time it takes to do each piece, which is the distance over velocity. dt is ds over v. Where v is due to gravity, how fast you're going. The lower you go, the faster you are. Okay? And ds is the piece of length, which is the square root of the piece of length in the x and the piece of length in the y square. Okay? So this is the problem. For what function y of x, this is the least possible.
Repeat circle.
It's close to a circle, but it's not a circle. It's not a circle, it's not a parabola, it's not a cubic. It's a shape that is called the cycloid. The cycloid. What is the cycloid? Well, the cycloid, this is what you find we're doing, is this shape. So it's the shape. If you have a wheel in your bicycle, and you look at when you put air in it, in the wheel, where the valve is, okay? What is the motion that the valve does while your bicycle rolls? Well, imagine that you start with the valve at the floor, okay? And imagine we are doing, this is the floor. So what will it do? Well, it will go up with the wheel, it will get to the top of the wheel, and then it will come down to the floor. And then it will go back again, and back again. As the wheel rolls, one point in the edge will go up and down, up and down, up and down, okay? That shape of one point on the wheel that is rolling is called a cycle. This is called an inverted cycle, because instead of going to the floor, to the floor, to the floor, this will be the shape if you will hang the wheel. You will hang the wheel from a rail, and you will roll it on the rail. Okay, so I will take a wheel, and I will roll it so that it goes towards the right. So the point that was here, now is here, later is going to be here, and eventually it's going to go back to the floor or to the frame. Okay? This shape is not a parabola, it's not a circle, it's called a cycle. The cycle is simply the term for wheel. The Greek word for wheel is cycle. That's why we call it bicycle, two wheel. Okay? So the equation of this, you're gonna find it. It has to do with basically this this result, and this is the shape. This is how the point.
Hello?
Hello? I
Y'all
couldn't hear
sound just getting
anything.
messed up.
I couldn't hear anything.
Dr. Ben, we lost you. I can't hear you, but you might be able to hear me.
I can hear
Yeah, I
Andrew.
can't hear either.
Oh, no.
Something's up with Dr. Ben's
April Fools.
Dr. Ben's audio.
Is he still teaching?
I think
I don't
so.
know.
Dr. Ben, we cannot hear you.
Oh, is there a text box?
Yeah,
Yeah.
there's a text box.
He's still teaching.
Okay.
Me?
Yeah.
Yeah.
I'm put out.
Oh, yeah. I was talking about Lola. She just like
Yeah.
looks at nothing like she just didn't.
Is it
Oh,
your
hold on. I'm
mom?
going to send it right to him.
Wait, how are your seminar going?
Did I lose the sound?
Oh,
Yeah,
Ah, there we
yeah.
go.
there we go.
there you
It
go.
looks like I lost the sound.
Yeah.
Did I lose the
Now I can
sound?
hear you.
Yeah, we couldn't hear you for the last 2 minutes.
I can't hear you.